Okay, excellent. I mean, I've got a timer if we can't use it. Just
Maybe you could give us like a,
I'll give you
like a 10-minute, 5-minute kind of thing.
Yeah.
Sorry.
That's fine, not a problem. Okay.
Just let me know when.
All right, well, as soon as we get everybody in, we'll go ahead and get this session started. All right. So now that Pat's in the room, that gives us official okay to move ahead and get this first session started on planning and programming tools. The question that we really want to answer here is, how do you visualize the planning and program process from data collection to performance monitoring? And we've got three exciting speakers. Our first presentation is from Federal Highway on highway externalities, the Inequity identification tool. Victoria, Dunleavy joined FHWA as a data scientist statistician nearly 3 years after working at the International Monetary Fund. Possessing a master's degree in business analytics from George Washington University, she is a leader of data management, inventory storage, and dissemination initiatives. Victoria is passionate about data analysis, big data, AI, and enjoys promoting different methods for improving policymaking processes through data visualization. And Thor Dodson is an economist with the Federal Highway Administration, the Office of Policy. He works on the Externality Cost Assessment Tool, or ECAT, the National Highway Construction Cost Index, the NHCCI, conducts benefit cost analysis review of highway projects for discretionary grant programs, and provides support for a variety of projects in the Office of Transportation Policy Studies. Let's welcome our speakers.
Thank you, everyone. So I'm Thor, I'm an economist. This is my colleague, Victoria, statistician. So we work in the Office of Policy, and today we're going to talk about externalities of highways, specifically some tools we've developed recently to visualize the cost estimates, as well as the spatial distribution and trying to quantify the actual equity of those exposure to negative highway externalities. So who are we? We work in the Office of Transportation Policy Studies. That's part of the Office of Policy and Governmental Affairs. We have a wide variety of backgrounds, including economics, operations research, engineering, transportation planning, statistics, political science, public administration. You know, we're in a very cross-sectional space, so we really lean into a lot of these backgrounds. It really helps us do what we do, which is a lot of research. We conduct research into transportation policy, legislation initiatives, as well as implementing and facilitating these through strategic planning. We develop a wide variety of tools and methods to support the decision making. Some of these tools include, we've worked on the highway cost allocation study, examining the relationship between investment, transportation performance, economic productivity, as well as truck size and weight policy, mile-based user fee, emerging transportation policy issues, a wide variety of interesting projects related to transportation. So we do this a lot for agency leadership, the transportation secretary, as well as other administration officials, and we also respond to congressional committees that make requests for our office. So what is our purpose today? We want to provide you an overview of the Externality Cost Assessment Tool, ECAT. We'll showcase the ECAT results dashboard, a place where we're hoping the results can be easily accessible for use by practitioners and planners. Then next, we'll show an overview of the work we've done applying ECAT for equity analysis, specifically the Inequity identification tool, which is a mapping platform to visualize the results we found. So what is ECAT? Externality is sort of an economic jargon term. It means in this case, we're talking about quantifying the negative impacts from the use of the highway system that are caused by, but not fully paid for by, different classes of highway users. So here we're thinking about what are the side effects of highways? Costs generated from highway use that the users are not themselves bearing. So we talk about noise, air pollution, crashes, and congestion, costs that affect people that aren't actually doing the driving or use of the highway system. So to get these estimates, ECAT brings together various model results, elasticities, and data. And it was originally designed to support the highway cost allocation study, looking at the cost allocated to different vehicle classes. But it can also support tax policy, benefit cost analysis, discretionary grant reviews, and transportation regulatory analysis. So what can ECAT do? Fundamentally, it can produce outputs to support policy decisions and project cost analysis. And it can do this in terms of external total cost per category, average cost per VMT, and in some categories, the marginal cost per VMT. It can break these costs down by state, by vehicle type, by highway functional class, as well as by rural and urban areas. And due to the inherent uncertainty in some of the models and parameters that are used to generate these estimates, we have a range of low, medium, and high scenarios. So a brief overview of what we have so far is noise pollution, which we estimate the total cost is around $11 billion, although we had a symposium in the last couple of days where we heard that cost may be a lot higher if we use a different methodology, which we're looking into. But currently the way we do this is we translate traffic volumes and speed into noise. So we look at the noise coming from highways, and then we use what's called the hedonic approach, or the indirect valuation, where we're assuming that people are internalizing the cost of this noise through their valuation of the housing market. So there's a large literature on this looking at what is the change in housing prices with exposure to different noise levels, and we use that as our basis to estimate the cost. Although we're exploring looking at the direct cost, because there are a lot of studies looking at the health impacts of exposure to noise over time. The next category is air pollution. This is a much higher magnitude so far. We estimate it's around $215 billion. And we do this through a combination of EPA models, MOVES, which allows us to get the emission rates from vehicles, as well as a model called COBRA, which can simulate the health costs from a change in ambient air quality. So we use our traffic data combined with emission rates to look at what is the impact on air quality, and then what are the health costs of that air quality. And the costs are very sizable. Additionally, we also calculate the cost of greenhouse gas emissions using MOVES, which estimates the emission rates for greenhouse gases, as well as the interagency social working group social cost of carbon estimate. The next category is traffic crashes. This one's a little more straightforward, although by no means simple. We look at the total number of crashes, both fatal and non-fatal, and we have a variety of techniques to monetize those crashes through the value of statistical life, as well as quality of life adjusted years. Congestion, we go segment by segment, looking at volume to flow capacity equations to estimate what is the delay on different traffic segment or road segments based on the traffic going through there. And then we have a value of time to monetize that. And we're also currently working on a method for estimating barrier effects. That is the cost generated by highways physically separating areas where it's difficult to cross or move around them, as well as the barrier effect presented from heavy traffic, because that can deter trips. It can be extra time or extra travel due to the physical difficulty of crossing busy roads. And this is well known as an impact that divides communities. So Victoria is going to take over next to show you the ECAT results dashboard. And our goal here is to make these estimates of the externality costs easily accessible. This can enable comparison of costs across states, across urban and rural areas, and across road types, as well as across different vehicle classes. And the cost is in per VMT format, which facilitates easy use and benefit cost analysis. If you can estimate the impact on VMT, something like induced demand or change in traffic loads. Okay.
Thank you, Thor. I think it's not showing on the screen.
Can you like right click and do duplicate screen?
No, it was showing before. I think it's something.
So you're just not seeing it on,
Yeah, I don't see it here. So the presentation was fine, but I just want to share the website.
Just a second, we'll see if we can.
I think you can try and minimize this window.
No, that, it was showing everything before.
I know, I think we should change the setting.
To what?
Victoria, let's try it.
So as we enjoy the wonders of technology. Okay. See if, all right, we are. Thank you.
Okay, here you can see the ECAT dashboard. And on the right top corner, you can see the tabs that we have here that will be your first tab to read about the ECAT dashboard, the methodology, and as well as the option to download the data from the Data Hub website. So here you can download the data and work on your own. But let's go back to the dashboard, to the home page, and let's explore the first, that we have two views. We'll have a graph view and a table view. And then here you see we have the ribbon of filters, and we'll start with the first filter, which is the state filter. We'll pick a couple states as well as the national. The next is the cost category filter. We currently have 5 externalities, 5 costs that you can choose from, which is delay, emission cost, noise cost, air pollution, and crash cost. For the first examples, let's pick noise cost. Then we have functional system class. Interstate, freeways, expressways, other principal arterias, minor arterias, major collector, minor collector, and local roads. And the classification is based on speed, uninterrupted use, land access, and mobility. And next filter is the vehicle type. We have motorcycles, passenger cars, buses, light trucks, single unit trucks, and combination trucks. In general, the bigger the car, the more cost it can cost. So if we choose the passenger cars, single unit truck, combination truck, we're gonna see our graph already populated on the bottom. So, but let's move to the next filter, is the unit filter. We have a cost per mile, as well as the total cost in million miles. Next filter is the area. We have a weighted average, which is overall option, urban areas, and rural areas. And the last filter is the cost range, which ranges from low, mid, to high. We usually use the mid range, and for different projects, we can use low, which is 80% of the mid, or the high range, which is around 120% of the mid rate. As you can see that the graph, the middle graph will show you the cost, and the bottom graph is going to show you the annual VMT. And if you want to look at annual VMT based on the functional class, you can just click on the functional class up top, it will change in the bottom. Let's go back and look at the graph itself. So right now you can see how functional class can contribute to noise. For example, minor and major collectors contribute more to the noise than the interstate. If we switch to the urban area, we will see a difference. We'll see a difference in the noise cost as well. It's going to be much higher. So we're going to move some of the vehicle types, and we only look at the passenger cars. We can easily see how a functional system contributes to the noise cost based on the different states and based on the functional system class. So some of the other principal areas contribute more to the cost, as well as some states can contribute more to the cost than the other states. And let's explore our second example. We'll go pick some other states. We get our states in, then we'll select the next cost we're going to look at is the pollutant cost. We will add the local road and the functional system class. And the rest filters will stay the same. So right now you can see that how the functional system class contributes to the air pollution cost. So it's pretty much functional system class contributes at the same level, even for different states. So let's add some more vehicle types, like single unit tracks. We can see the same pattern, as well as the combination tracks. So now this graph is a little bit crowded. It's a little bit hard to read the numbers. That's why we built in a table view, which is color-coded, can help your eyes easily to identify the functional class or the state or the vehicle type that contribute most to the pollutant cost. Okay, and with that, I'll go back to the presentation and Thor will talk some more about the noise.
Thank you, Victoria. So as you can see, our goal there is to, sorry. So our goal there is to make the variety of external costs accessible. Because you see with a large number of filters, the costs vary dramatically across states, across vehicle types, and having all of that in a huge table is a little difficult to process. So we wanted to make that in a form that's easier to look at for practitioners. Maybe you're only interested in one state, but you want to compare across road types, or you want to compare across vehicle classes. All of that functionality is built into the tool, and so we're still seeking how to fine-tune that, because there's a lot of dimensions to showcase. So next I'd like to talk about the work we've done over the last year applying ECAT to equity analysis and the distributive impacts. So ECAT estimates the cost of externalities from highway use, but we wanted to extend this to estimate who is affected. And we've expanded the tool to analyze equity for noise and air pollution, because those are more easily localizable. You know, we know where they're coming from, we know how far they go, so we have a much better idea of who is actually affected by that. The general approach is we estimate where does the exposure occur, and then we attribute the exposure, the cost of that exposure, to demographics of intersecting ACS census block groups, which has a population at a very fine spatial detail. Why do we want to do this? So we've already seen the cost of these externalities can be very substantial. Highway noise and air pollution, they're produced by users, but they affect people who are not actually using the system. This can result in adverse health effects, reduced cognitive performance, and diminished quality of life. And it stands to reason that households near highways absorb more noise and air pollutants. And if subpopulations or demographics tend to live near highways due to historical policy, gentrification, structural inequality, social capital, or other reasons, then highway externalities are contributing to inequity. And we believe the results, methodology, and the mapping tool can support efforts to target inequities for mitigation from the negative externalities of highways. So how do we do this for noise? So first, using our traffic to noise equations, we estimate the distance each sound level reaches from each highway segment. So if anyone's familiar with the HPMS data set, it has down to 1/10 of a mile often length of segments. And then we have the traffic data for those roads. So we estimate the noise coming from that road. Then we use the ACS data to look at the housing density near the road segment to estimate basically how many people are affected by that level of noise. Then, using the hedonic pricing literature on what is the cost of the noise reflected in the housing price, we can estimate the total cost from noise for each highway segment. Then, we allocate it to different demographics based on the relative percentage within the intersecting census block group. So if a highway is intersecting a census block group with 20% non-white population, for instance, we would allocate 20% of the cost to the non-white population. So here we're implicitly assuming that within the census block group, all the populations are evenly distributed throughout the space, which of course is not always true. There's usually clustering in neighborhoods which can be actually closer to the highway or farther away. But until we have better detailed population data, this is the best assumption we can make. So finally, now that we have the cost allocated to each demographic for each highway segment, we can aggregate over a larger area. So say over a county, over a state, or even over the whole nation, and calculate what we call the noise equity ratio, which is the percentage of costs absorbed by a demographic divided by the percentage of the population of that demographic within that area we've aggregated over. Crucially, if this number is greater than 1, then that demographic's absorbing more than we could call the fair share. They're absorbing more noise cost than their share of the population. Less than 1, the reverse. So for instance, if you can imagine the entire population was randomly distributed through the whole country, there was no patterns, then this ratio would be 1 for all demographics. But as we see, that's not the case. So first, pay attention to the left 2 most columns. We can see that the white population absorbs significantly less than what we could call the fair share of noise cost, around 0.86. So it's 14% less than the fair share. While the non-white population, which is an aggregate measure of all the other demographics, absorbs about 38% more noise than the fair share. We can see how that's distributed across different demographics. And then the last 2 bars show us that we look at non-poverty and poverty, we see a similar effect. Non-poverty is absorbing less noise. It's around 0.97, I believe, while poverty is absorbing about 1.13, 13% more than what we call the fair share of noise. So this is aggregating over the whole nation. We can also aggregate over the states and see how does this inequity vary across states. You can see, like on average, here we're only comparing non-white in the top set and the white in the bottom, and generally non-white tends to absorb more than the fair share of noise. We can also look at county levels. So here each column represents a different county in Texas. The orange square is the non-white value, the blue square is the white. And I want to point out, on average, non-white is much higher than 1. It's like 1.22. But of course, this varies across space. Last point about this is it's really an urban thing. Over 90% of the noise damage we're observing is in urban areas, which is a little bit of a rough measure. There's always suburban, exurban, various things. But this is largely because of this noise damage depends on the density of houses near roads, the amount of vehicle traffic, the speed of the traffic, and the traffic composition. That is how many trucks versus cars, because trucks generate a lot more noise. So in order to make these results palatable and understandable for practitioners who actually want to do something about it, we've made this mapping application to visualize the distribution of highway externalities. It combines the cost of the noise with the equity calculations to easily see where are the high cost noise roads, and then where are the inequities. We developed some case studies highlighting the historical legacy of highway placement. This tool can enable pinpointing of roads with high externalities for mitigation, and it can also screen potential highway projects to understand the impact on equity. Is there an existing inequity there? Is this going to make it worse or better? And I know that noise is one of the sort of smaller externality costs in magnitude, but noise is actually reflective of all the other externalities. Even though the magnitude may be different from the other categories, the distribution tends to follow where the traffic is, which is where the noise is. So we believe this noise equity analysis is actually very reflective of other highway externalities and how they're distributed across demographics, across space. So briefly, I'll just talk through a couple case studies before we show the tool. Here on the left-hand side, we're looking at the equity ratio values for the non-white population at the county level. So darker red means higher, greater than 1. Blue means less than 1. And we can zoom in on an area we've identified that has a high noise inequity towards the non-white population. In this case, around Birmingham and Tuscaloosa. And then the second graphic, we've switched the layer to the percentage of population of non-white population at the census block group level. And then the roads, the thickness of the lines is showing the magnitude of the noise costs. And you can see a visual correlation between where there are a high percentage of non-white population and where the highest noise cost roads are. Similarly, we can look at, I was looking at a history of communities that were severed by highways and identified Akron, Ohio as one of them. And then sure enough, looking at the tool, we can see there's a high noise inequity there. And then you can pinpoint, which roads are causing it, which neighborhoods are really being affected by the high noise cost. We've also built in a set of filters. So for instance, you can filter which counties are shown to have a noise equity ratio higher than a certain value, as well as filtering for the magnitude of the noise damage for each road segment to understand, which roads should we target, which areas have high inequity. So in the bottom right, we can see we filtered for roads that have greater than $500,000 per 1/10 of a mile, which are clearly good candidates for some sort of noise mitigating procedure. I have a couple more case studies, but for the sake of time, we'll jump right into the tool.
Okay, here's the tool, and first we're gonna be looking at the noise equity ratio layer, which is color-coded from the blue to red, and the 10 is represented the middle like 1. So we can easily identify the counties with noise equity ratio more than 1, which is gonna be the red ones, and you'll have a nice table here that will tell you exact number for the county for the non-white equity noise ratio, as well as the darker blue counties will represent a non-white equity lower than 1. And as a default, we're going to be looking at non-white option. So if we go back to let's turn this off, we'll go back to the actual layer. We have a symbology where you can actually pick a demographic, non-white by default, but you can choose any of what we have here. As well as Thor mentioned, we have a filter. So you can filter a non-white equity ratio if you want to see everything that's over 1.6, so really high. Or if you want to look at the non-white damage in annual dollars, in dollars, so if it's more than $2.5 million, you'll see the counties for that. And you can use both filters with and statement. So looking at the counties with 1.2 and the non-white damage higher than 2.5 million. So next layer is the noise damage layer. It's also color-coded by the bins. So the lowest bin would represent the annual noise damage less than 100, and the darkest, thickest line, bin number 7, will represent the noise damage over 1 million. So we also have an option to filter the noise damage by functional class. We want to look at the interstate, minor, major collector, or if we want to look at the bins. For example, we're only interested in noise damage over 1 million, and then if we will zoom in a little more to see the roads, we can actually see what roads contribute to the noise damage over the million, and if we want to look at what functional classes, we can play with this filter, and you will see when the highway disappears and appears back, or local roads not here. There's some minor arteries. So we can also quickly look at the urban areas. With all of that, we can see that the noise mostly concentrated in the urban areas. And let's quickly I show you how Thor find the Syracuse by using both the noise damage and the noise equity ratio layers together. So turn them on. Actually, I'll turn this off. Go back to Syracuse here. Zoom in on it. I'll turn this layer off, turn the road layer on. We'll go back to the filter. We're only interested in the ones that more than 500,000. And we can clearly see the roads. We also have an option here to switch a map to like an imagery map. If we turn this layer off, zoom in really in on the communities there, we'll be able to see what community is affected by the road. And with that, if we want to explore more about the population on the communities, we're going to turn the population layer on. It's also color-coded. It's also, you can choose the symbology. It's set for non-white as a default, but you can choose any other population. And then we can see amount of non-white population that varies from the light purple, which is 0.2%, to dark purple, which is around 1%. So I'll turn the road back on, just to see how it looks from far. And I think this is it for the presentation demonstration. I'll give it back to Thor. Oh, yeah, I also want to mention that we have the home page. If you want to do any further research on that, we provided the future service options to download the data and play with the data. And we have kind of a story that tells you more about ECAT and the inequality identification tool. Okay, now back to Thor.
All right, so thank you very much for your attention. We're very excited to showcase this tool. We're not quite ready to publish yet, should be sometime next year. But we're very open to questions, especially feedback on applications. How can we make ECAT work for you? Does this seem like something that's relevant? Any suggestions, of course. This is very important to us as part of understanding the full range, not only the benefits, but the cost of highways. So I think there's a lot of concerns about, who is benefiting while who is bearing the cost of the highways. And we believe this is an important tool to try to shed light on actually quantifying that discrepancy. Thank you.
Excellent. So we've got a couple of minutes for questions.
I have a pair of questions. One is, given all the assumptions that are included in this model, does it make you at all uncomfortable that people are going to zoom really far into this map and come to you and say, hey, you said this amount of noise, but I experienced this amount of noise?
So obviously, yeah.
And then the second is with the ECAT, you have the states and you have urban rural. Are those values summarized for the entirety of that state, or are they like the noise summarized up from the calculation?
So on the results dashboard, the results are summarized from the state. So we're basically using like the average housing density near those road types, which is a little different than what we're seeing in the actual mapping tool where we're calculating it for individual highway segments. But as far as actually discrepancy between on-the-ground experience, I think this is definitely an issue, but it's always an issue when it comes to spatial data. I mean, for instance, I have a sound meter on my phone, and I live near 695 over in Capitol Hill, and I've measured it, and I've been like, this doesn't really match our model predictions at all. But so there's definitely questions on, how far does the noise go? What's the actual experience level? What's the impact of things like vegetation and noise barriers? But there are some techniques to try to account for these, which is some of the work we'll be doing to update before we publish. So I think broader though the question is, are there systematic differences that are going to throw it off in specific areas? Otherwise, I think we're going to be pretty close to the reality on the ground. Mm-hmm.
You actually answered my question. It was just about the effect of vegetation and noise barriers.
Yeah, and that's something where there's a bit of mixed research. I mean, some people say noise barriers can actually end up bouncing the sound, so it goes farther and just changes where it's impacted. But I think there's a lot of research on actually combining noise barriers with vegetation above it that can absorb not only the noise, but the air pollution as well. So that's definitely one of my preferred mitigation strategies.
And when do you think it's actually going to be published?
Sometime next year. Uh-huh.
So, I think you focused a lot on the, I guess, the noise pollution. You talked about the 5 other characteristics. Is there going to be a way to kind of hone in on some of those? I have a couple of questions. I'll kind of get them all out.
Yeah, yeah.
Then the second was, so you did say, I heard it over there, you said states, and then it kind of got into like urban and rural areas. Like, how do you define, is the state going to be the smallest geography that you use? Or at some point, will you be able to kind of get down to a county level? Because I think there's definitely going to be a lot of information sharing or benefit to the users from that perspective. And then the last question, probably, based on this data, what's the time frame of the data that you're actively to the age? What is the frame of the data that you're using right now?
Let me go in reverse order. So it's sort of like like a modern snapshot, I would say. We use a combination of 2016, 2017 highway data, and we use the 2019 ACS data. And then we have some 2017, 2018 sprinkled in there for things like crash data and stuff like that. So I would say this is like a modern snapshot. And then the second question, let me go back to the first question actually. So for the other externality categories, part of the challenge there is it's not as easily localizable. So for instance, we've done some work with the air pollution, but our tool we use to estimate the cost, COBRA from EPA, that only estimates the cost at the county level. And we're really interested in going to a finer grain than that, especially because there's large difference in population distribution within the county level. But the challenge there is to get accurate estimates of, what is the air pollution exposure near highways? There's a lot of research that suggests it's very significant. The health costs can be a lot more than the ambient air quality changes, particularly within 500 meters. And we're pursuing a couple approaches to try to tackle that, but it's definitely a challenging part. We haven't done any work yet on crashes or congestion, but we think we could do similar analysis of where the crash is occurring, and then estimate what is crash risk exposure, something like that.
All right, thank you very much.
Oh, we have one more for the state versus county. Sorry. So we do look at the census block group level for the populations, and we have these equity ratios at the county level. Currently, the ECAT estimates in terms of the cost externality are only at the state level, and that was partially because of the design for the highway cost allocation study. So we could go finer grain if that's needed.
All right, thank you very much.
Thank you.
Thank you.
And while we bring up Grace's presentation on yellow to green, optimizing school bus routes to reduce the carbon footprint of local high schools, it's my pleasure to introduce Grace Yan, who is a junior at Morgantown High School, okay? In West Virginia. She's been a bus rider since she was in kindergarten and is very passionate about the environment. These interests prompted her to do research on bus route optimization to help reduce the carbon footprint of school buses. She hopes to be able to raise awareness for air pollution and climate change with her work. She's very interested in the intersection between math and science. Grace Yan.
Good morning, everyone. Thanks so much for this opportunity to present my project, Yellow to Green, Optimizing School Bus Routes to Reduce the Carbon Footprint of Local High Schools. My name is Grace Yan. Is there a way to?
Go forward.
Yeah,
The big button in the middle.
it's not working.
Wonders of technology. This did work. Can you?
I can advance.
Well, let's see. No. So, yeah, you'll just, for the moment, tell him to advance.
All right, next slide, please. So I'm a junior at Morgantown High School, but as you can see, I've been a bus rider since kindergarten. I love being able to talk to my friends every morning and afternoon on bus rides. Next slide. But as I entered high school and started driving, I realized that our buses would take roundabout, inefficient routes to school. I like to consider myself an environmentally friendly person. Next slide, please. But I knew that these inefficiencies in the routes were causing increased greenhouse gas emissions into our atmosphere. I'm also from West Virginia, the US's second largest producer of coal and known for having problematic air quality and pollution in many areas. So I wanted to research ways to make our buses more environmentally friendly. The first thought would be to upgrade our buses to an all-electric fleet. But obviously, this is very expensive and is not feasible for most school districts. Next slide. I recently discovered, just this morning at breakfast, that President Biden has devoted over $1 billion to turning our school buses electric, which is amazing. But until that happens, I wanted to find a low-cost, practical solution that could be easily implemented. Next slide, please. I also recently got my driver's permit, which means Google Maps is my best friend. Google has created very in-depth routing algorithms that optimize for distance, time, traffic conditions, and more. So this gave me an idea. What if we could optimize our school bus routes to make them more environmentally friendly using Google Maps? To get started, I wanted to visualize what the full bus routes look like to see if they're really as inefficient as they felt from my perspective as a rider. I have to wake up every morning at 6 a.m., so maybe I was just too tired to realize that our buses were actually really optimized. So I went to my school's website where bus route information was posted and focused on my own high school since it encompassed the largest geographical area and over 3 times as many buses as other nearby schools. I manually plotted all 388 bus stops in this map you see here, and this was encompassed by the 30 morning buses at my school. I color-coded each of the routes, and looking at the data, one thing I noticed was that the routes seemed to be very Frankenstein, as if new stops were being added to old routes year after year. The objective of this study is to create an accessible, zero-cost solution to reduce the carbon footprint of school buses by optimizing school buses for decreased travel mileage. So the first step in my process was to extract the GPS coordinates of each bus stop from its address. I created a Python script that automatically extracted these coordinates and used them in this human-in-the-loop component, which allowed me to override any locations that couldn't be parsed by my code. I then fed these coordinates into an algorithm that interfaced with the Google Maps API, which is Google's library for their routing algorithms, and also what powers the Google Maps app on your phone. I fed these coordinates and was able to format them into Google Maps API query URLs, which I then queried Google to find the most optimized route. Next slide. Then my code outputs the optimized route as well as the calculated total travel distance and duration. I repeated this process for all 30 buses at my school across multiple days and averaged the results. So here's a case study that really shows the essence of my project. Our school buses start at our county's transportation center on the left, and of course end up at our school. The bus goes to the route. Okay, there's gonna be a lot of clicking, so just a warning. But it goes to the route, and as you can see here, the numbers, which are a little hard to see actually, the numbers show the pickup order. So our bus goes through this route in this little loop, down to the bottom bus stop. So it goes down here, down to the bottom, and then to school. And so here, again, on the left, we have the original route, which shows the bus starting from this stop, curving around and going down, and then finally to school. But what the optimization tells us is that if we instead start our buses at this stop and curve around and to school, we would be able to save 3 miles and 7 minutes for just this route. Here's another example bus route, where essentially flipping the pickup order can save us 4 miles and 6 minutes. Here, our buses still start at our transportation center and currently go to this stop, curve around to school in this big loop. But instead, if we take our buses to start from this stop and go this way directly to school, we would be able to save these distances and these times. Next slide, please. Here are the results for all 30 buses at my school. The yellow bars show the original route, while the green bars show the optimized ones. And the graphs show the total calculations for the distance and duration. Looking at this data, I saw that some of the routes were already pretty well optimized, but others could be greatly improved. So I conducted a paired t-test to compare the travel distance in miles of the original and optimized routes. Here are the results. I found that my optimization was able to significantly decrease the total distance of these routes. Thanks. This table shows the carbon emissions reduction of the top most optimized buses. It turns out that 15 of the 30 buses saved greater than a 0.5 kilogram reduction in carbon emissions. Next slide, please. Okay, thank you. I also conducted another paired t-test to compare the carbon emissions reduction of the original and optimized routes. And here, I was also able to show that my optimization significantly reduced the carbon emissions from these routes. So I found that for just my school, using these optimizations, we would be able to save 20 metric tons of carbon dioxide from being emitted into the atmosphere each year, which accounts for 5% of the total carbon emissions. And over the course of one school day, we would be able to save 76 miles in over 2 hours. Throughout the entire school year, this would account for over $10,000 in fuel cost savings. And keep in mind, this is just for one school. With these results, I decided to reach out to the Monongalia County Director of Transportation to present my findings. He was super excited about the idea and invited me to present at the County Board of Education. Thank you. At the County Board of Education meeting. The board said that this was something they would love to explore in the following years. This gave me the idea to reach out to more individuals in charge to see if this could be something we could implement on an institutional level. I reached out to senators in my district as well as those in the state's capital and presented my findings. One senator was very excited about how my optimizations would be able to save not only tax dollars, but also reduce greenhouse gas emissions. Another said that this was a model that should be considered in all 55 counties in the state, which is very exciting. But most importantly, these senators were kind enough to introduce me to those that ran the school bus systems in their area. And I was reached out by the State Director of Transportation. I was able to present my results and discuss the implementation of my optimization in our schools and state's buses. We even got a pilot study confirmed and approved for my county to test and will hopefully expand to other counties in the future. In fact, I've already started working with another county, Barber County in West Virginia, to help optimize their routes. The map shows all 1,022 stops of the 29 buses in Barber County. And I've already helped them optimize a couple of their routes. And we are going to discuss the implementation of some of these routes, and hopefully we'll be able to test them very soon. The final part of my project was an idea I had to expand the accessibility through visualization. I built a website called yellowtogreen.org that's a carbon emissions calculator and bus route optimizer. It takes in a list of bus stop coordinates or addresses and automatically optimizes them to find the best route. It prints out the total route length and the corresponding addresses, as well as the calculations in the carbon emission savings and distance savings for comparing the optimized and the original routes. Essentially, everything I did in this project was put onto this user-friendly website, and I have a quick demo for how it works. I'm not sure if I play it. Oh. Hey everyone, here's a quick demo of my website, Yellow to Green, that lets you automatically optimize school bus routes. It's pretty self-explanatory. All you need is your bus starting location, your bus stop addresses, and your final destination, or school. You hit plot points and wait for all the points to plot. Then you can click Optimize. Here it gives you all the results with the current and optimized route length and duration, new stop ordering, and the corresponding addresses, as well as the savings per year of carbon dioxide emissions and fuel cost, making this a quick and easy way to turn your school buses from yellow to green. All right, thank you. All right, in conclusion, from start to finish, visualization has played an important role in this project. From confirming the original idea to analyzing the optimization results, we found that school bus routes can be optimized to reduce the carbon emissions. Using my algorithm, my school could save 20 metric tons of carbon dioxide emissions and over $10,000 on fuel each year. To put this in perspective, there are over 24,000 public high schools in the US. And this was all done by an accessible, low-touch, zero-cost optimization algorithm. I'd like to end with some acknowledgements. Big thanks to Mr. Gibson, Dr. Yoon, Miss Rhonda, Miss Pat Hu, and my parents for all their help. Here are my references, and that concludes my presentation.
I think this is a wonderful example, and her mom is actually here, so. This is exciting to see a student who has seen a problem and gone after a solution, found the solution, and found a really good way of visualizing how she's done it. So, questions?
Did you learn how the school, during your research, did you learn how they currently plan their stops? You mentioned a little bit earlier.
Oh, yeah. So I think when I talked with the director of transportation, the routes had just been there ever since our school had been created or started. But just like I said, year after year, if new students were coming from certain areas, they would just add stops to whatever route was the closest and what seemed like was the best idea. And so that was what created some of these Frankensteining of the routes and what caused these inefficiencies. I'm sure at one point these routes were really great, but over the years they had become less efficient. And so that's why I decided to target.
Have you looked into adding any more variables, such as changing a stop from one route to another, or trying to move the stop to see if putting it on a different around the corner might and add a small amount of walking time for the students might make it more efficient overall? So moving the waypoints as part of the
Yeah.
or moving them from route to route?
All right, great question. So actually, I do have a couple of limitations of the study that I wasn't able to consider. So I wasn't able to consider, of course, regrouping the bus stops because I wasn't able to present this project in a way that I thought would be easy to implement if I was able, like if I was going to propose that we change our bus routes entirely. I wanted to find a low effort change that would be able to be implemented, which is the first thing I was thinking about when doing this project. So I really wanted to focus on something that could be easy to do, low effort, that my transportation director would, easily agree to. So obviously, changing the routes, which would greatly reduce the emissions, and would also be able to consider taking out certain buses and reducing the number of buses, which would also help our greenhouse gas emissions. But another thing I wasn't able to consider was changing the parking locations of the buses. So if you look at the map, I don't know if we can go back to it, but the map showed that a lot of our buses started from the transportation center. And since the transportation center is our counties, it's kind of in a centralized location for all the counties, not just our school, or not all the schools in our county, not just my school. So I noticed that a lot of the bus routes were really far away from where they were being parked. And so if we could change where the buses were being parked, we'd be able to reduce the distance of the overall routes by pretty significantly.
One more?
Yeah. First of all, I'm really surprised that this research can be done by high school students. This is
Thank you.
Great research. And actually, it's not a question. It is my comment. When you consider school bus optimization to reduce the air quality, is great. But we also need to consider about potential crash risk, because we need to minimize the number of left turn events. Also, we need to minimize the crossing the street of the kids to minimize the crash.
Yeah.
Possibly, it will be your future research topic, just this to consider to minimize the crash risk when you consider optimizing the school bus routes.
Yeah, so one big concern, especially for elementary students, is crossing the road to the buses, right? Because you don't want them to cross busy roads. But I'm a high schooler, and this is exactly why I wanted to optimize our high school routes, especially since they are a lot earlier in the morning and it might be dark out. But for my personal bus, to get off the bus and go to my neighborhood, I do have to cross the road, and it's not a big deal for me and the high schoolers, especially since I noticed that my route in particular in my house, you can go down the road and curve around, and so it is a big U-turn. But I noticed that the high schoolers at my neighborhood would always just get off early and cross the road instead of waiting for the extra 1 or 2 minutes for the bus to curve around and then for us to get off. So I think I realized that our high schoolers, at least, maybe the parents, but not ourselves, really cared about crossing the roads. Of course, this is a big concern for elementary students, but for us, it wasn't such a big deal.
Excellent. One more back here.
Yeah, hi. First of all, I have teenage daughters, and you make me proud like a mom. But your initial, and I'm Grace with Esri, but your initial, and I like your name too. You initially wanted to reduce GHG emissions, right?
Mm-hmm.
And then I think you got the ear of the state. Is there talk now of implementing not just optimized routes, but implementing electric buses and an electric fleet? Has that been talked about?
I haven't heard too much from who I've been talking with about changing to electric buses. I wanted something that we could do for zero cost, would not cost us any money. And obviously, having a grant to change from electric to electric buses would be a great help to reducing our greenhouse gas emissions. But this is an optimization that can be done on regular diesel-powered buses, but also electric buses. I originally thought that, electric buses would be great for the environment, and that they are. But they do release half the amount of carbon emissions. So it's not like they're releasing no emissions at all. And so this is still something that could be considered in electric buses as well.
Very good. Thank you very much. All right, so our third presenter is David Hutchinson, who's going to be talking about visualization and transportation planning from visioning to performance measures. He serves as Executive Director of the Sarasota-Manatee Metropolitan Planning Organization. His multidisciplinary generalist background spans more than 30 years, combining policy, planning, public affairs, and program administration. He approaches regional transportation planning in terms of relationships to land use, infrastructure independencies, communities, and economic development, systems operations, safety, security, equity, and resiliency. So, welcome David, who's got some great visualizations to show you from his area.
Thank you, Frank. And Grace, in a few years, I can see you running the routes for Amazon or UPS or any one of a number of organizations. So great work. Talk about changing the world. That's how it's done. And whoever scheduled me after her. So I am going to run through a lot of examples of how a metropolitan planning organization uses visualization in our work. And I was told that I don't really have to explain to this audience what an MPO is, but I will at least tell you where we're located, south of Tampa on the southwest coast of Florida. We kind of had a storm go through there not too long ago. Luckily a little further south than it was originally projected to go. And our MPO is a 2-county MPO. We have a governing board of 17 elected officials from throughout the region, and we operate under the guidance and funding from the Florida Department of Transportation and the Federal Highway Administration, Federal Transit Administration. And when I hire staff, I actually do tell them that we're out to change the world. And Grace makes it look a lot easier than it seems to be sometimes. We operate under a variety of mandates that come from federal law and state statute and federal regulation. And our main products under these mandates are a long-range transportation plan that's about a 20-year look out into the future. What transportation facilities are going to be needed, what types of population growth is going to occur, where is it going to occur, where will jobs be located, and we develop a list of project priorities that are identified in that plan that get funded over time, and every year we update our plan in conjunction with the state funding program and produce a transportation improvement program. Our Unified Planning Work Program is our budget document. It's a 2-year document, and we have a public participation plan in civil rights assurances and a mandated congestion management process, which is now tied into the performance measure mandates that is one of the focuses of this symposium. This is just an example of how even in our budget document we incorporate visualizations, and this is the cover, and you'll notice there's no red on it. It's a budget document. We don't go into the red. The bicyclists that you see a bunch of modes listed across the bottom of the document, and we did not want them riding only uphill. Part of this route to transportation funding in our region has to be downhill. And in the fine print, we are using this document also to remind citizens and our elected officials of the value of this, the MPO process. So we actually added the statement that MPO collaborative process leads to billions of dollars in transportation projects. And our budget is about a $1.2 to $1.6 million a year. So, and sometimes people wonder why we do so much planning, and it's to get those billions of dollars of investment in. We through our long-range planning process, we have used a scenario planning and visioning effort that identified 4 different scenarios that were analyzed, and this was for the 2045 plan that we are currently implementing. We had consultants who worked on identifying existing population zones and what types of communities do we have within our region. And those are identified here, and those are mapped out. And you can see we have an interstate running the length of our region that connects us to areas north and south. I'm going to go through these slides, not super fast, but fairly fast. And the process identified these 9 land use types and scenario planning place types that we're focused on. And it's interesting, after this morning's presentation, I'm thinking we should have had 3 place types instead of 9 in order to simplify it. But I think as I go through this, you'll sort of see why we did what we did. And with each of these place types, we identified what does that look like, what to help the public primarily visualize what are these place types and what makes them up. And this was back when we held public meetings for our public outreach, and we would present to them, okay, what these mean when we're talking about them, and we would do that with visualizations that you can see here, and how close, what are the densities, and which types of places support transit, etc. It's somewhat typical planning lingo in many ways. So we talk about placemaking in urban transportation planning, and we wanted our audiences to have a visualization of what these different types of place types are. And much of our region is in the suburban space, so to speak, and you could say sprawl, actually, and we have lots of sprawl, and this is what it looks like. And we think that part of the value of the visioning was to help people understand what other types of places could be in the future to support transportation planning. We have a lot of rural areas that are somewhat undeveloped and lesser developed now, and the trend, though, is for the population to move further and further east, and for that sprawl that has been going on for the last 30 years at a high rate will continue. And this visualization, and for each trend, we analyzed what the impact in these zones would be, as far as how many jobs would be in each of these context zones, and where would the housing be, in which with the trend you can see, let's see here, that a lot of the housing was going to be in the rural residential and in the suburban areas, and the jobs were still going to continue to be in the urban corridors. So that's the trend scenario, and this is what it looks like on a map, where the green is turning yellow more and more as the rural areas get populated at low density. The second scenario that we looked at was, we're going to focus on supporting the economy. What would a transportation network look like? What would a community in the region look like if we focused on promoting jobs and enhancing growth along the I-75 corridor and in existing urban centers? And you can see that we still have a lot of rural growth, and a lot of the jobs are still in away from the housing. So our transportation system needs are going to continue to grow. And this, still had a lot more of the growth off to the west, but there was, it was one scenario that we looked at, and we looked at 2 others. One was focusing on environmental health and protecting the environment and promoting infill to a great extent, trying to get our local jurisdictions to adhere to what their urban growth boundaries are. And you can see that if we did that, there would be no new housing in the urban area and or in the rural area, excuse me, and that the housing in the future would be much closer to the jobs. And so that scenario protected much more of the green space and focused growth in the existing area. And then the last scenario was a focus on placemaking and connecting our vibrant places, and we have a few of them. You'll see some pictures in a while that show some of them, that focus on transit-oriented development and ensuring that we don't build a lot of roads. And you can see that housing and again, is not focused in the rural areas, so sprawl, the continuation of sprawl is stopped under vibrant places. And what we had to do is, this is another representation of some of these analyses. After the Washington Post graphics director spoke, I thought, well, this one's pretty complicated. But it shows the same things on one graph that you saw for each of the scenarios with the housing and jobs distribution changing. And you can see that households by place. Either way you look at it, we're going to have a lot more households in the future. We're anticipating our population going from a little over 800,000 to well over 1 million in the next 15 years or so. And we ranked the various scenarios on what their impacts to our transportation system would be, and you can see the results here. And we ended up adopting a plan that sort of took the best of all of the scenarios and put them into a future that identified places where we would focus on placemaking, corridors that we would try to enhance transit on, et cetera. And so these were visualizations that helped our public and our elected officials understand and adopt a plan that will move us to the future. And one of the tools that we used as we ranked these was performance measures. You know, we did drink the Kool-Aid. We believe in performance measures, and we think that they are helping us get funding for transportation projects within our region. You'll see some icons here that should look familiar. Some of them were developed by the state of Florida or Federal Highway Administration to represent some of the performance measures that we have within our region. We use lots of visualizations in our long-range plan and to help people understand what these various things are. Here's where the various types of projects are listed in our Unified Planning Work Program or budget, and we actually group them and tie them directly to implementing performance measures. We also have a series of fact sheets that were produced back when we were printing things and handing them out at meetings. And so for each of the performance measures, we produced a fact sheet to help illustrate what those performance measures are and what they meant and how we are moving towards progress in achieving the performance objectives. And we have an interactive website. We're not going to try to go to it right now. Perhaps if there's time and somebody wants to, or you can go to mympo.org and check these out for yourself. But for each of the performance measures, we have an interactive site now, and we're moving towards using live data where that interactive dashboard will be even more useful in the future. And let's see here, click, there we go. So our Transportation Improvement Program, which is the 5-year work program that goes hand in hand with the state's Transportation Improvement Program, is interactive and online, and people can zoom in and click on an area or click on a specific project and pull up information about that project. In our tip, we use color codes to help people visualize programs that are already funded, at least partially in the work program. Those are the green projects that are supposedly and hopefully moving forward through what we call the production pipeline. We also use different color codes for some of the funding sources and/or programs that we identified in our cost feasible plan. Another area that we've made use of, I'll let this play and try to talk over it, is public outreach. And for the last few years, we've partnered with other MPOs in Southwest Florida, and we have produced a Gulf Coast Safe Streets Summit. We rotate that around, and we had the pleasure of doing one that was virtual. And so, but part of that, we wanted to give people some of the tours that were usually available when you have in-person ones. Oh, let's see, I needed to go to do a click, but can you do a click right on that graphic? And we'll get a little bit of a taste of this. We won't play the whole 7-minute tour. I bet you this is royalty-free music. And if you want to just skip forward towards the end, there's a little bit there, perfect. Different places around our region. We'll go on. And this is still on our website if anyone wants a tour of Sarasota or Manatee County. Oh, let's see. How do we go to the next slide? Thank you. We also came up with so we were able to pivot using a lot of technology and virtual tools to continue to have public outreach and during the second part of our LRTP development. And one of the tools that we did was we did a low-cost, in-house created program called Tuesday Traffic Jam. Here's an example of that. I think this one plays automatically, but it may not. It might need a click.
How can the community get involved and participate in the Destination Zero Action Plan?
The easiest and most direct way for people to get involved and participate is to visit the Destination Zero page on the MPO's website. From here, they'll have the opportunity to learn about Destination Zero, the development of the action plan, and perhaps most importantly, provide us with
This is an edited version of this episode.
And an
they were
interactive
usually
map that
about
allows
5
people
or
to
6
identify
minutes
and
long,
comment on locations
and we
where they're
send those
concerned
out
about
every week.
safety.
Not all of them involve video or live, but for a while there, that was one of our key ways of conducting public outreach and sharing information.
How can the
And recently, we were asked to present a presentation regarding the artsy roundabouts of Sarasota. And as part of the community safety program and resiliency program, we've really gotten into roundabouts in our area. And this is a quick video that shows you some of our places in downtown Sarasota, and it's a nice visualization. It may need a click. So as you can see, we've got pretty pictures that always help with visualizations, and some of the guidance that if you are able to go to Frank's session tomorrow afternoon, our moderator, he will tell you that you have to simplify your message even though you're talking about complex data and complex topics. And you have to consider your audiences, like who are you talking to? And we do that, and you have to tell a story. So hopefully you're getting a little bit of the story of our region and how we use visualization in our processes. And let's see, I think the next slide would be good. It's there we go. So these are some of the larger roundabouts that are still under construction, and the visualization tools that have been used in sharing what's happening with the public are impressive. The visualization artists do a great job. I think the maintenance of traffic engineers do a great job as well, because these this particular intersection that is becoming a roundabout handles about 35 to 40,000 vehicles per day, and they are still handling that traffic during construction. So it's been very creative. That's a whole nother topic. We have a few planning studies underway. You heard a little bit about Destination Zero. That's our implementation of how do we get to zero deaths and serious injuries on our transportation system. And as we shift to promoting transit, we are looking at some of the options that might make transit more efficient in some of our key corridors, and those have also used some visualization tools. I think that one might need a click also to run. You can see that this one has to do with signal prioritization for transit. We're trying to do a demonstration project with the state and our 2 counties and their 2 transit systems on one corridor, focusing initially on 5 intersections where we could implement transit signal prioritization. We could go on to the next slide. That's kind of a typical engineering. We also used a lot of data of origin and destination information using the streetlight program, where we were able to visualize where people were going on bicycles and walking that will help determine some trail alignment recommendations, and the ability to visualize that makes it much easier to make decisions and helps support those decisions at the elected official level, which they're one of our key audiences. And we currently have a resiliency study underway. As you see over on that right, this is what your traditional surge maps look like related to various types of hurricanes. And I think it's hard for people to visualize those, because even people who live in a surge zone, they've not had flooding before, so they think they're fine. And the fact is that just south of us, and even in some of the areas on that map, and even inland, some of the areas that are not normally underwater, you can see to the right over here, the Myakka River is normally pretty dry. It is a river, but it is not anywhere near as flooded as you see in that lower photo from space that NOAA has already released. And it was just incredible the amount of flooding that took place, not just in our area, but all across the state. No one expected that much. Of course, that hurricane brought nearly 20 inches of rain. If you ever think about an older mobile home in an area that's subject to hurricanes, I'd recommend against it. And you can see some of that flooding on the right as well. And so sometimes the images that come from these catastrophic disasters can be really important for future planning and evacuation efforts to get people to understand what catastrophic damage really is. So I know that's another big topic at TRB. And so we anticipate incorporating some of the newest information from Hurricane Ian into our resiliency plan. We're constantly evaluating the success of our outreach efforts, and there are some new guidance documents that have just been released about public participation plans and community participation. So we'll be studying that and incorporating that in, and of course we're always looking at how do we better reach out to historically underserved communities. And I think that's about it for me. Thank you very much.
So before we have questions for David, one of the things I'd love for you to do is just turn to the person next to you, and what were big takeaways from this session? What do you think? And you've got 2 minutes. I'm going to give you a 2-minute warning, but just what are your big takeaways from what you've heard today? Go. Yes. Yeah, it seems to work here. I think the practical part is they're going to ask, yours is the latest, so you'll still I hear. You have 1 minute left. Thirty seconds. Yeah. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Thank you. So, any comments back as to just some high-level takeaways that you had? Any questions for David? Sure. I will say that was one of the things I was most impressed by this was the use of photographs, the visualizations, the infographics. This is a really visually stunning package of very complex information that they've really done a good job of, kind of using it to engage their community. And especially when we've got a pandemic going on, that's changed the way public involvement's happened, and I think they got a great package for that.